Greetings. So welcome to today's class. So from today we will get started with the state space representation, which is another representation of the governing equations of the class of systems under study. So if we recall, at a very broad level, in control design, we have the transfer function representation and the state space representation of dynamic systems. So what happens is that, when we look at the transfer function representation, the governing equation of the class of systems under study, right, take the form of linear ordinary differential equations with constant coefficients. So what we do is that we apply the Laplace transform to the governing equations and get the transfer function, right? So we go to the complex domain and do the analysis, and that's what we learned till now, right? So now the question is, what is the state space representation and how do we design controllers based on that? So from today's class, we will start looking at the state space representation. So in the state space representation, we are going to stay in the time domain and we are going to do the analysis in the time domain, right? So that is going to be a big feature of this. So what is the core or central idea behind the state space representation? What we do in the state space representation is the following, right? So if we have an nth order ODE as the governing equation for the class of system under study, what we do is that we rewrite the nth order ODE as a set of n first order ODE. Okay, so that is the basic idea, right, behind this state space representation. So we are going to stay in the time domain, but however, we are going to rewrite the nth order ODE as n first order ODE, right? So if you recall what happened in the transfer function, we applied the Laplace transform, and we sort of went from the time domain to the complex domain, and we converted the ordinary differential equation into an algebraic equation, right, involving S. So in the state space representation, we are going to stay in the time domain, but however, we are going to do this, rewriting of the nth order ODE as n first order ODE. Then, in order to facilitate that, okay, we identify what are called as state variables, okay, in this process. So what are state variables? These are those variables, whose knowledge at every instant of time completely characterizes the system, okay, or the system response. Okay, so that is the state variable. Okay, so for example, let us say we have let's say a car moving along the longitudinal direction, right? Let's say we know its position and speed, right? So those may be enough to characterize the state of the car, right, at each and every instant of time, right? So those are what are called as state variables. So the basic idea behind the state space representation is for us to identify as many state variables as the order of the system, and then rewrite this nth order ODE as n first order ODE. Okay, so let me explain this entire process using an example. Okay, so we will consider our standard 1 degree of freedom mass spring damper system. So let us say the block diagram is this. So we apply a force F of T. There is a displacement X of T. Let's say the spring constant is K and the damping coefficient is some C. So if you recall, the governing equation of this system is mx double dot T plus Cx dot T plus Kx of T is equal to F of T. Okay, so that's the governing equation of this system. And if you recall that the Planck transfer function T of S is going to be the Laplace of the output divided by the Laplace of the input, which in this case comes out to be 1 divided by ms squared plus cs plus k, right? So these are things which we are already aware of, right? And if we look at this as a system, this mass spring damper system, we know that the force f of t is the input, and the displacement x of t is the output. Right? So as we already know, the transfer function is the ratio of the Laplace of the output to the Laplace of the input, right? Under zero initial condition. So that's what we get as the transfer function. All right. Okay. So now what do we do, right? So to write down the state space representation of the system. So please note that the value of n as far as this governing ordinary differential equation is concerned, it's 2, and the value of m is 0. So if you recall what were n and m, n is the order of the highest derivative of the output term in the governing ordinary differential equation. M is the order of the highest derivative of the input term, right, in the governing ordinary differential equation, right? So those are n and m. So as far as this particular what to say, system is concerned, the value of n is 2. It's a second order system, and the value of m is 0, right? Because there is no derivative of the input term on the right hand side. All right. So these are the facts which we already know about. Now, moving forward, what do we do, right? So what are the steps that are involved in writing down this state space? The first step is we need to identify n state variables. Okay, so we identify as many state variables as the order of the system. So the order of the system is n. So what we do is that, like, we identify as many state variables as the order of the system. So in this case, the n is 2. So we have to identify two state variables. So let us choose the two state variables as x1 of t to be x, and x2 of t to be equal to x dot. Okay, so typically state variables are denoted by the character x with a subscript underneath it to denote the number associated with the state variable. It is just a sheer coincidence that the symbol x is also used for denoting displacement in this example. Okay, so that is a coincidence. All right. So, but in general, the character x with a subscript is used for denoting a state variable. All right. So we choose position or displacement and speed, right, as the two state variables in this particular case. Then what we do is that, like, we evaluate the first derivative of each state variable. So that's what we need to do. Okay. So first time derivative of each state variable. So what we do is that, like, we have x1 t equals to x of t, x2 t equals to x dot of t. So we take the first derivative, right, of both these state variables. So what happens? So if we take the first derivative of x1, we get x1 dot t, right? That's going to be equal to x dot of t. And immediately we can observe that this x dot of t is x2. So the basic idea is to rewrite the first derivative, right, of each state variable in terms of the state variables and the inputs themselves. Okay, so that's what we need to do. So what we do is that, like, we essentially are going to rewrite this first derivative of the state variables in terms of the state variables themselves and the input term. All right, so that's what we have done here. So this is the first equation. Then the second equation is in terms of x2. X2 dot will now become x double dot t. That's going to become, so how do we get x double dot? Okay, so for that we go to the governing equation. Okay, so we please see that we can get x double dot from the governing equation, because see, if we just take what to say x2 dot. See, how do we get this? By the way, so you can see that this is x2. So you take the time derivative on both sides, right? So you get x2 dot to be equal to x double dot, right? So I'm sure that's understandable, right? So once we get x double dot, if you look at the governing equation, we can immediately rewrite x double dot as minus k by m x t minus c by m x dot of t plus 1 by m f of t, right? So I'm sure all of us can immediately recognize how we got this, right? So just to clarify, we can see that from the governing equation, we have mx double dot t to be equal to minus kxt minus cx dot t plus f of t, right? From here, we get this equation, right? So we divide towards the m, we can immediately get that equation, right? So I'm sure all of us can immediately recognize what we have done. Okay, so now we are all set. Okay, so we have identified as many state variables as the order of the system, first class. Then we have taken the first derivative of each state variable, right? So that is the second class. So these two equations, 1 and 2, okay, form what are called as a state equation. So state equations are first order differential equations involving the state variables and the input that essentially characterize how the state variables evolve with them, right? Because if we integrate these equations, we are going to get the time evolution of the state variables. Okay, so that is the idea behind the state equation. So in this particular case, if we integrate the two equations, we will get displacement and speed, right, at each and every instant of time. So now what we do is the following. Okay, we define what is called as a state vector. Okay, the state vector or the vector of the state variable, which is denoted by x with a tilde underneath it. So typically, vectors are indicated in lowercase boldface font, right? So since I am not, I can't write boldface on in this medium, so I am going to use a tilde underneath the character, right? So yeah, so if I am using a lowercase boldface font in the time domain, I'm going to refer to a vector, right? So this vector is going to be essentially, let's say, a column vector with the two elements being x1t and x2t. Okay, so that's what is called as a state vector. Okay, so in general, it is of dimension n. Okay, so this is a vector of dimension n. Okay, in this particular case, the value of n is 2. So that is why the dimension of this vector is right. So this is an n-dimensional vector in general. So then what do we do is the following. We then rewrite x dot, or we write x dot, okay, which is going to be x1 dot t and x2 dot t. So what we are going to do is that, like, we are just going to stack these two equations, right, that we have derived just a few minutes back in terms of a vector OD. Okay, so that's where we are getting to. So we are going to rewrite in this form. Okay? So let me write the structure and then I'll explain. All right. So this is the structure in which we are going to look for. So if we look at this particular structure, so the first state equation is this, right? X1 dot equals x2, right? So if you look at x1 dot equals x2, so suppose if let's say I put 0, 1, and 0 here, right? So you will see that if I do the matrix vector multiplication, I will get x2, right? So I'm sure all of us can agree to that point, right? So what I have done, I have written the governing equation for x1, all right? Yeah. So in terms of the state variable and the input there, okay? So now we go to x2 dot, right? What is the equation for x2 dot? x2 dot is here. So now if I write x2 dot is minus k by m x1 minus c by m x2 and then 1 by m f of t. How did I get this? Please note that this I can rewrite this as minus k by m x1t, right? Because why? X is x1 minus c by m x2t, because x2 is x1 plus 1 by m f of t, right? So that's how we can rewrite this particular equation, the second equation, right? So we can essentially get this particular equation, right? So you can immediately recognize that this is a vector first order differential equation, right? So, and this is what is called as a state equation. Okay, so this equation, which is a first order ODE, but a vector ODE, right? And this characterizes how the state variables evolve with time, is what is called as a state equation. I hope it's clear how we got this, right? So if you look at these terms, this is the state vector x, right? This is u of t in this particular problem. And this 2 by 2 matrix is what is called as a state matrix. So I am going to use a capital letter with a tilde underneath. Okay, so typically matrices are indicated in uppercase boldface form. Okay, so here I am using an uppercase character A with a tilde underneath. Okay, so that is what is called as a state matrix, which comes here. And by in general, it is a n by n matrix. Okay, in this example, it's a 2 by 2 matrix. In general, it's a n by n matrix. Okay, so this column vector, which is of dimension n, is what is called as the input vector. Okay, so it is characterized by the character b. Okay, so b with a tilde underneath it is of dimension n, and essentially this is a column vector of dimension n, and that's what is called as the input vector. So this equation is written in compact form as x dot equals axt plus dut. Okay, so this is the general state equation in a compact form for a single input, single output system. All right, so this is the state equation. All right, I hope it is clear how we have chosen the state variables and then taken the first derivative of the state variables and collected the terms together, right? And essentially put in the put them in a compact vector ODE form to get this state equation. Okay, so this is the first equation. So why am I saying this is the first equation? Because we are not done yet, right? Because as far as the state space, as far as the system is concerned, ultimately we want to relate the output and the input, right? So we have not returned the output yet. Okay, we have only returned the connection between the state variable and the input. Okay, that is what is obtained through the state equation, right? So now, if you look at the output y of t in this example is the displacement x, which due to the choice of the state variable is x1, right? Because the first state variable x1 is chosen as the displacement. Now, what we do is that we once again write it in terms of the state vector. Okay, so the state vector is x1 and x2. So now, if I want to get x1 from the state vector x1 and x2, we can immediately observe that if I take the dot product with 1 and 0, right, I am going to get x1. Right, so I hope this is clear to all of us. Right, so if I take the dot product of the column vector 1 and 0 with the column vector x1, x2, I am going to get x1 as the answer. So once again, we know that this is the state vector x. This vector is now called as the output vector. Okay, denoted by C. It's called as the output vector. This is once again of dimension n. All right, and this equation is what is called as the output equation. Okay, and in general, the output equation for a single input, single output system takes the form P dot x plus dut. Okay, so this is the general form for the so-called output equation. Okay, in the state space representation. So the state equation and the output equation put together form the state space representation, right? So what does the output equation give us? It gives us a relationship between the system output and the state variable and the input. Okay, and you can immediately observe that this DU term didn't come in this problem, right? Because this DUT term is what is called as a direct transmission term, and this comes into play only when m is equal to n. Okay, so if m is less than n, okay, as in this problem, it doesn't appear, okay, in the output equation. So that's an important point to remember. So please note that the direct transmission term, or essentially DUT, comes into play, okay, only when m is equal to n, okay, not otherwise. So please remember that, right? Okay. So now the one important thing, right? So before we go ahead, is that like in many references, okay, you will find the C dot X being written as C transpose X. Okay, you will get the same answer. So see, what people will do is that like they will essentially write this vector output vector as a row vector, and then like they will take the product with the state vector x1, x2, you will get the same answer, right? X1, right? But I prefer using the dot product notation, okay, rather than the transpose notation. You can use either one, okay, whichever suits you, you can use it. Okay, so that's the clarification I wanted to give you. So going ahead, so these are the state equation and the output equation. So to summarize, the state space representation. State space representation of an nth order LTI causal dynamic system can be written as the following. Okay, so it has two equations. So what happens is that like we can write the state equation. It is a vector first order ODE as x dot equals AXB plus BUT. That's the state equation, and y of t equals C dot xt plus DUT. Okay, so that's the complete state space. Okay, so this is the state space. So the state space representation has two equations. Okay, so once again, it has the state equation, all right, and the output of the measurement equation. Okay, some people will call it as a measurement equation, some people will call it as the output equation. Okay, so these are the two equations, and the set A, B, C, D is what is called as a realization of the system. Okay, these are some terms that you would encounter, right, as we go further in the state space. So you have the set A, B, C, D. That's what is called as a realization of the system. Okay. Okay. So this is the state space representation in general, and we can immediately observe that the relation, right, between so once again, if you look at a system, right, and we have an input u of t and we have an output y of t, in the transfer function representation, we directly related y and u, right? However, in the state space representation, the relationship goes through x, okay, which is internal to the system, right? So, or it characterizes the internal dynamics. So, for that reason, some people will call the state space representation as an internal representation. So why do they call as the internal representation? Because the output is related to the input through the state vector. Okay, so for that reason, it is called as the internal representation. On the other hand, in the transfer function representation, the output and the input are directly related to each other. So for that reason, it's called as the external representation. All right. Okay. So that is the state space representation. Now, what about the equivalence between the two representations, right? So essentially, we want to figure out what is the equivalence between the transfer function representation and the state space representation that we have derived. All right, so let's look at the equivalence. Okay, so let us take the Laplace transform, right? So let us take the Laplace transform of the state equation and the output equation, one by one, right? State equation and the output equation. So if you take the Laplace transform, what will happen is that the Laplace transform of x dot will be x times x of s minus x0. Okay, that's going to be equal to a times capital X of s plus b times u of s. Okay, so that's what we have. All right. So now, because we want to calculate the transfer function, okay, we assume all the initial state variables, the initial conditions to be zero. Need not be in general, but the definition of the transfer function says that we need to take all the initial conditions to be zero, right? So that's why we have this. So now, if we collect the terms of x, right, and rewrite this above equation, what will we get? We will get si minus a. Okay, so it won't be s minus a, but then like we have to write it as si minus a. And what is this I? I is an identity matrix, okay, of dimension n. Of course, it's going to be of dimension n by n, right? So because A is a n by n matrix. So what is this identity matrix? Identity matrix means all the diagonal terms are of 1, the off diagonal terms are all 0. So like this, it will keep on going, and you will have 0 everywhere other than the diagonal element. Okay, so that will be a diagonal matrix, perspective, an identity matrix, right? So you have 1 along the diagonal of the matrix. Okay, so that's the identity matrix I. So now, assuming that si minus a is invertible, so what we will have is that like x of s will be equal to si minus a into du of s. Okay, so we have this expression. Then what happens is that like if you take the output equation and apply the Laplace transform, we have y of s to be equal to c dot x of s plus d times u of s, right? So we are just taking the output equation is an algebraic equation, right? So the Laplace transform becomes pretty simple. Okay, so we don't have any derivative terms then. Okay, so we get c dot x of s plus d times u of s. So we substitute for x of s, we will have c dot si minus a inverse d u of s plus d times u of s. Okay, so that's what we have. So if we collect the terms involving u of s, we are going to get y of s to be equal to c dot si minus a inverse p plus d times u of s. Okay, so this is what we have. All right. So I hope this derivation is clear, right, to everybody. So we can get this the relationship between the Laplace of the input and the Laplace. So immediately we can observe that the term within the square bracket is the Planck transfer function. Why? Because recall that as far as the definition of the Planck transfer function is concerned, it's the ratio of the Laplace of the input to the Laplace of the output under zero initial conditions. Right? That's what we have done. Right? We have taken the Laplace transform of the state and the output equation, applied zero initial conditions, and got a P of S, right? In terms of the state space realization, right? So this essentially gives us that a very important equation which shows the relationship between the state space representation and the transfer function representation. So the state space, the transfer function is going to be C dot Si minus A inverse B plus C. Okay, so that's what we are going to get. So you see that we are going to have an equivalent relationship, right, between the transfer function and the state space representation. Okay, so so if we know the state space representation, we can always find the transfer function, right? So then we are going to observe something even more interesting, right, between the two representations going ahead. All right. Okay. So what I want you to do as an exercise is to check this for the mass spring damper system. Okay, example that which we have been typically considering. Okay, so what do I mean by that? Okay, I'll just explain that. So I'm leaving this as an exercise to you. Please check this expression for the mass spring damper system. So going back to the mass spring damper system, we know that the transfer function of the mass spring damper system is this, right? 1 by ms squared plus cs plus k, right? So this is the transfer function of the mass spring damper system. So if you look at the what to say, realization for the mass spring damper system, the state matrix is 0, 1 minus k by m minus c by m. The input vector is 0 and 1 by m. The output vector is 1 and 0. The direct transmission term d is 0. Okay, so what you need to do is that like substitute it for all this. Okay, so for the mass spring damper system, P of S is going to be equal to 1 divided by ms squared plus cs plus k. Okay, and the state matrix as we have derived, it is 0, 1, minus k by m, minus c by m. Okay, the input vector is going to be 0 and 1 by m. The output vector is going to be 1 and 0, right? And the term d is going to be 0. Okay, so there is no direct transition. Okay, so what I'm giving it as an exercise is that like substitute these values of a, b, c, and d into this above expression, and you should get 1 by ms squared plus cs, right? So that is the expectation, right? So please do that, all right? And just verify that expression. Okay, fine. All right. Any questions still here?
No, sir.
Okay, good. So now, as the next step, let us look at the state space representation of a MIMO system. Okay, LDI MIMO system. Okay, so one advantage of the state space representation is that like it can be easily used to essentially represent the dynamics of multi-input, multi-output systems also in a nice form. Okay, so let us say there are MIMO system. Okay, so let us say there are P outputs. Okay, P greater than 1 and Q input. Okay, in general for a MIMO system, P and Q are going to be equal to 1 for a SISO system, right? So, but what happens in the case of a MIMO system? So, in the case of a MIMO system, the state equation takes the form x dot t equal to, you will still have n state variables, it will be a x t plus, now the quantity b will become a vector. Okay, so because the input is a vector, right? So consequently, u is a vector of dimension q. Okay, so this is an input vector, right, of dimension q, right? Because it has now there are q inputs, right? So consequently, the quantity b is what is called as the input matrix, and we can immediately see that the size of the matrix now is going to be n by q, right? Because ultimately the order of the state vector is n, right? So there will be n first order ODEs. So we need to have n, what to say, to be the dimension of the vector bu. So obviously there should be n rows in the matrix B and q columns, right? So for the multiplication to be appropriate, right? So that's the state equation for the memo case. If you look at the output equation, so in general, let's say if there are t outputs, the output will also now be a vector. So y of t, so that will be a matrix C multiplying the state vector, okay, and a matrix D multiplying the input vector D. Alright, so this is how the output equation will look like. So now C is what is called as the output matrix, okay, whose size will be P by N, right? Because we have P outputs, so we need to generate P outputs from a vector which has N entries, which is a state vector. So since T multiplies X, for the matrix multiplication to be valid, the dimension or size of C should be P by N. And D becomes what is called as a direct transmission matrix. And the size of this matrix is going to be equal to P by Q, right? Because we have P outputs, right, and Q inputs, right? So consequently, the size of the matrix is going to be P by Q, right? So that's the direct transmission matrix. So in this case, A, B, C, D, which are all matrices, okay, is what is called as the realization of this. Okay, so this is how the state space representation for a matrix, sorry, for a memo system will look like. Okay, so I hope that is clear. All right. So now the question becomes, what do we have, right? So we have learned about the state space representation that involves rewriting an nth order ODE as n first order differential equation. So we identify the n state variables, and then we take the first derivative of each state variable, and then we rewrite the first derivative in terms of the state vector and the inputs themselves, and then we form the state equation and the output equation, right? Which together give us the state space representation. And we have also seen an equivalence between the state space representation and the transfer function. Okay, so we will learn more about these in the upcoming classes. We are going to build on this. What I am going to do now is that I'm just going to complete this class with a few definitions, right? That all of us are already aware of. It is just that we are just recapping, right? So the first definition that I'm going to write is about the eigenvalue and the eigenvector of a matrix, right? So lambda and V, okay, indicate the eigenvalue the eigenvector of matrix A, okay, is, okay, we multiply the vector V with the matrix A, that should give us lambda times V. Of course, V is non-trivial, okay, so that is very, very important, okay, so the vector V cannot be 0, right, so then there is nothing for us to solve, right, so essentially we have AV to be lambda V. Okay, so then lambda is called as the an eigenvalue of the matrix A, and V is the corresponding eigenvector. Okay, so this is the definition of eigenvalue and eigenvector. Okay, so we have to remember this. So from this definition, we can immediately see that we will have lambda I minus A V to be equal to 0, right? So we just take things to the other side, right, and take V common, right? So this is once again we introduce the identity matrix, because I can't write lambda minus A, right? Lambda is a scalar, A is a matrix, right? So I have to write lambda I minus A, right? So that's what we do. So this is of the form. Let's say we call this matrix as, okay, not B. Okay, so let's say some A1. Okay, so the matrix A1 is a matrix lambda I minus A B equal to 0, and B is non-zero. So if from basic linear algebra, we know that whenever we have a product of a matrix and a vector, right, which is non-zero to be 0, the only thing is that, like, the matrix is a singular matrix. Okay, so that means that its determinant is 0. Okay, so that is the consequence. So immediately we can see that we'll have determinant of lambda I minus A to be equal to, okay, so that is an important expression, right? So this is an expression that we commonly use to calculate the eigenvalues of a matrix, right? So I hope it's clear how we do that, right? So typically, if someone asks us to calculate the eigenvalues of a matrix, we do determinant of lambda I minus A equals 0, or the determinant of A minus lambda I equals to 0, right? So this is how we get it, and then we go to this expression and find the corresponding eigenvector. Okay, so we can get the eigenvector from this expression. All right, so that's, we will do a few examples. Okay, going down the line as to how to calculate the eigenvalues and eigenvectors, right, for a given matrix A. So then, if we look at the definition of an inverse, right? How do we get the inverse of a matrix? So please note that, let's say if we have a matrix A1, the inverse of the matrix A1 is what is called as the adjoint of the matrix A1 divided by its determinant, right? So that's the definition of the inverse of a matrix, right? So what is this adjoint of the matrix? Adjoint is essentially the transpose of the cofactor matrix, right? And we form the cofactor matrix by essentially replacing each element with the determinant of a lower order matrix, which is removed by eliminating the corresponding row and column, right, at whose intersection the particular element is located in, right? So that's how we calculate the inverse of a matrix. Okay, so we are all familiar with this. I just wanted to recap these definitions. Okay? So we are going to use these definitions as we go further. All right. So please remember the definitions of eigenvalues, eigenvectors, how to calculate the eigenvalue and eigenvector, and the definition of inverse of a matrix. All right. Okay. Fine. Okay. So are there any questions on what we have learned today? So if not, what I will do is that I will close today's session here, and then we'll continue in the next class. Thank you.